Good morning. We are beginning chapter 6 today, and we are going to cover section 6.1 and 6.2 in this vodcast. At the end of the vodcast, I'll work two problems, 16 and 20 from chapter 6, that will help you get started with your work. By way of explanation, when we start talking about chapter 6 in general, we're talking about some extremely mathematical concepts. And we're getting into an area of study called computational fluid dynamics. And really, even though you have a lot of math as engineers, you've been up through calculus 2 at least, you understand partial differential equations, you probably understand also that a lot of differential equations and partial differential equations are not actually solvable in the analytic sense. And it turns out that with fluid mechanics and fluid dynamics, that is the case for a lot of very typical flow regimes. For example, a turbulent flow, transitional flow, that sort of thing is not really analytically solvable. So what we're going to do is we're going to talk about the general math. We're going to learn a lot of definitions that help us describe fluid flows. And then we're going to look at a couple, not in this lecture, but in the last lecture of this chapter, we're going to look at some solved types of fluid flows. So we're going to make things that are very, I wouldn't say, well, kind of simplified, but also things that are very straightforward and types of flows that we see commonly that are solvable. So with that, let's talk about section 6.1 and 6.2. All right. So here in section 6, well, chapter 6 in general, deals with the idea of differential analysis of fluid flow. And this is compared to the finite element analysis that we talked about in chapter 5. So when we talk about the differential analysis of fluid flow, we are talking about one single point. So we look at either a particle of fluid or one infinitesimally small place in a fluid flow regime, and we analyze that particular position. And then if we want to sort of gin it up, if it's a smooth function, we integrate over some time period or some area or whatever is most applicable. But in general, the differential analysis of fluid flow talks about relationships. And by that, of course, I mean mathematical relationships that apply at a point in the fluid. Right. So once again, we're talking about this very specific condition. The other thing is that we may need to know things such as how velocity, like in the past, let's just talk about velocity. If we had a pipe flow and we had a mass flow rate going in and mass flow rate going out, right? And we might talk about the velocity because we know that Q, which is volumetric flow rate, times rho is equal to mass flow rate. And that in the case of an incompressible fluid, in other words, if rho is constant, then we could also say that Q is constant, Q in equals Q out. And then we could further say that velocity times cross-sectional area is equal to Q. So if we have the same cross-sectional areas, we can also say V is constant. All right. Now, that is a very general term because if you really think about fluid flow in a pipe, it's not everywhere the same. So what we're really talking about here is an average velocity. You can have a velocity profile that starts at 0 at the sides where the fluid particles are adhering to the sides of the tube to some sort of a Vmax out here. Or you could even have swirls and eddies and things that are not really running perpendicular to the entrance or the exit of that pipe. So what is V right here, for example, at this particular particle? Well, we can't answer that question using, we can't use that question using finite element analysis. We can only answer that question if we look at a single point. So to get into some ideas of how we're going to analyze fluid flow, we need to talk about some definitions. Okay, a viscous flow has viscosity, and inviscous means viscosity may be neglected. Now, it doesn't really mean that it's equal to zero, because all fluids are to some degree viscous. They have some amount of viscosity. And if you remember, we talked about dynamic and kinematic viscosity, but we talked about mu, for example, is the viscosity. Right? And there's a relationship. Now, all of these are definitions, so I'm kind of building this into our lecture. But for a Newtonian fluid, we know that this relationship, and I'm not labeling these axes on purpose, we'll talk about that later, but basically we have a relationship between shear stress and shear strain, where when one is zero, the other is zero, and where the slope is constant, and the slope of this line is equal to the viscosity. That is a definition for a Newtonian fluid. Now, any non-Newtonian fluid is just something that doesn't behave that way. So in other words, with the same axes labels, maybe the fluid doesn't run through zero. That is called a Bingham plastic. You may have something that runs through zero but slopes like this. You may have something that runs through zero but slopes like this. Or you may have something that breaks over, all right? So in other words, anything that doesn't behave this way is non-Newtonian. And we'll break that down later on into what type of non-Newtonian. But Newtonian means exactly the same thing every single time, is that we have an intersection at 0, 0. That's where we have our y-intercept, and that the slope of this line is constant. So the line is straight. And that means the slope of this line is the viscosity. The slope of each of these lines is the viscosity as well, but you can see that it's a little bit different in terms of what that looks like, because some of them are not straight. In this case, we have a straight line, but it doesn't go through zero, so we have, instead of just being m, we have a y is equal to mx plus b type equation, and so forth. All right, so by way of definition, Newtonian is just like this. Non-Newtonian is everything else. All right, now the reason that we talk about viscous and inviscous regions is that if you have fluid flow through a conduit, like a pipe once again, there is often a situation that the velocity profile tends to be parabolic in these types of situations. But there is an area near the boundary, and in the boundary region, viscosity is important. So we have to use some terms. We have to develop a viscous flow regime. But quite often, in the center or away from the boundary, the viscosity becomes less and less important. And so we can analyze it here as being inviscid. So we can look at fluid flow from a fluid element kinematic point of view as having two different areas, one of which has a much more complicated mathematical construction or analysis than does the other part. And once again, we are getting into this area which is referred to as computational fluid dynamics, which is not easily analyzable using methods of mathematics, of analytic math. So we often have to use numeric methods, and this is really computers and modeling have really advanced this field. Modeling, which we'll talk about in chapters 8 and 7, I believe, is also referred to as simulation. So we'll take a look at that later on. Now, in order to study these elements, we need to talk about the velocity and acceleration fields. And we've already discussed this, but we're just going to revisit it. And one of the things that we're going to talk about is the fact that the vector v for a fluid can be broken down into Cartesian coordinates. And we commonly refer to the components in the x, y, and z direction as u, that would be the velocity component in the x direction, little v, velocity component in the y direction, and w, the velocity component in the z direction. And then similarly, if you recall, for acceleration, we had to take into account the time rate of change and the convective rate of change for each of those components. And this is a rehash of what we've already done. Okay, so in other words, we could break it down into the component of acceleration in the x direction is going to equal the time, or the unsteady part, plus my u partial and my v partial. This is u, it looks like a y. Sorry about that. And then similarly for a sub y and a sub z. So to express acceleration in a concise manner, we can say that it is the material derivative of velocity with respect to time. Or we can also say that if we use this idea of material derivative, that it's the partial of the function with respect to time plus the convective terms once again. All right. And then last but not least, we can recognize that we have a del operator or gradient with that convective direction. And if we take the dot product of those with that function, we can have another expression for velocity. So all of that is pretty mathy. But what we need to think about then is, in terms of the velocity and the acceleration, is that there is a relationship between velocity, acceleration, space, and time. And there are different ways that we can move a fluid. We can translate it, which is just a straight motion, or we can rotate it, which means that it's going to spin. Now, another part that we may need to think about is, I'm going to see if I can come back here and find your textbook and put it up on the screen while I'm talking about this, so that you can refer to this. But I'm referring to page 300 in your textbook. So, textbook for chapter 6, putting it up on the podium PC. All right, and here we go. All right, so here's a description of motion. General motion means that we have a translation with a rotation and possibly these deformations as well. So we can have a translation, and we can also have a linear deformation, which means that the size and shape of that fluid element changes. So it may have started out looking like this. I should point over here. It may have started out looking like the solid box and elongated or stretched out to look like this. So if we take a translation, a linear deformation, then we have a rotation, which we discussed, and an angular deformation. We can come out with this general plane motion. Now, one thing to remember is that if the fluid is incompressible, there's really not going to be a a deformation that's going to change the size of the particle. If the element started out with this particular, I'm drawing it, it's drawn here as an area, but it's really a volume, isn't it? That means that the volume can't change if there is no change in the density. So if it's incompressible, that term is going to be equal to 0. But what we see on the next couple of pages then is a mathematical discussion of what this means. And so there's a couple of things that we need to think about. Here on page 302, we have a translation. This is just a pure translation. In other words, we start here at point O, and point O moves in the x direction, and it moves in the y direction to point O0. Now, something that's kind of important to remember, speaking of this idea of dilation, and I'm going to write this down so that you'll have it in your notes, but if you have the dot product, hang on, the document camera, there you go. If you have the dot product of the gradient with the velocity, that product is the dilation rate. But if you have the gradient crossed with the velocity, that's what's called the vorticity, which has to do with the spin. And we'll discuss that in general. But I want you to have this specifically in your notes because they look similar mathematically, but you have to remember that vectors multiply two different ways. We multiply dot product, which is a scalar. They also call it the scalar product. And we have the cross product, which is a vector product. So this is scalar multiplication, and this is, or the scalar product and the vector product. All right, so we'll discuss what those mean a little bit more, but I want to be really clear that as we go through the textbook that those two things are significantly different from each other. All right, so here what I want to make a point of is the change in volume, the del V. Remember, V with a little bar through it is volume, and we have the fluid element, the du dx, u being once again the velocity component in the x direction, and the time element and the volume. Del x, del y, del z would be the volume element. And so we have this that just comes out to give us this dot product, which I just talked about earlier. But that is referred to as the volumetric dilation rate. Now, the thing, as I also mentioned, here in your textbook, they have in a blue box off to the side, that the volumetric dilation rate is 0 for an incompressible fluid. So this dot product, or the sum of these three scalars, these three partial differential equation components, will be equal to 0 if it is incompressible. It's a very important simplifying assumption that comes up a lot in our discussions. All right, so continuing on down, when we talk about the angular motion and deformation, it's important to notice that this term omega is the angular velocity, and omega here is written as a scalar. So this is the scalar component of the angular velocity. So that's going to be in radians per second, for example. And it's a limit as the acceleration with respect to the differential acceleration with respect to time, it approaches that in that limit. Now, this is just some more simplifying assumptions, but this is what we're really getting at, is the fact that if we start with some sort of a rectangular fluid element and it changes in angular shape, then we have this sort of an angular deformation, and we can have an angular rotation as well. The other thing is that if this entire thing occurs in the plane of the paper, omega is going to be a vector that's either coming into or out of the paper or the board, depending on whether it's a positive or negative vector. So the other thing is, for those of you that have had solid mechanics or mechanics of materials, you recognize this as being a shearing strain. It's the exact same concept. It just happens for a fluid when a shear occurs that you have a relationship based on the viscosity between the shearing strain and the shearing stress, and that also causes movement of a fluid. So it's a little bit more complicated, but it's the same idea. All right, So here we go, and here's a couple more definitions that we need to talk about. If we have, I'm going to put this back on the document cam, the vector omega is going to be the components of omega, and this is for three-dimensional. What we drew on the page was just what's going on in terms of if all of our motion is in the plane of the page, and then the vector omega is either going to be in or out of the page. But we know that in general, omega can be anywhere because the motion can be anywhere. But this is referred to, of course, as the vector angular velocity, and it's measured in radians per second, or sometimes it's just written as seconds to the minus 1. Now, there's a little bit more math that goes into the idea that omega is equal to 1/2 of what's called the curl, C-U-R-L, of the velocity. And the curl just means what we've talked about so far, the gradient crossed with the velocity, which is referred to as the vorticity. So we can also say in words that angular velocity is the same as 1/2 times the vorticity, or we could call that the curl of the velocity. Okay, now what that means for us is, if you recall, a cross product looks like this. In order to analyze it, we have to set up a determinant. Where these are the components of this, these are the components of this, and we have ijk, and then of course the half outside. Okay, well, we have a new variable then that would be the vorticity. Well, this is, I'm sorry, that's not actually the vorticity, that is actually the angular velocity, and 2 times the angular velocity is called vorticity, which is indicated by this letter. Okay, now vorticity describes rotational characteristics. I know that's very general, but it's something that you may be called upon to calculate. Or it may be something that you need to think about whether it can be simplified or ignored, eliminated due to being negligible in a particular fluid flow. All right, so if we take a look at everything relates, this is the other point that I want to make, is that everything relates through the components of velocity, u, v, and w. So here is a situation, example 6.1. Shows you a good example where you have a component of u and a component v and a component w. So in other words, v vector would be equal to u times I plus v times j plus w times k. So we find omega x using the partials, omega y using the partials, and omega z using the partials. What we find is that each of those is equal to 0, and that's the definition for the flow to be irrotational. Okay, now it's also a two-dimensional flow field. But this is a good example of where the rubber hits the road. This is the type of computation that you do out of this very complicated math theory. All right, so continuing on with that idea, I'll get some more paper here on the document cam. We've talked about that. We need to just have a couple of more definitions. Del y is the shearing strain. of a fluid. And the way that we define it is change from a right angle. So that means that if the fluid element used to look like this, and now it looks like this is the original angle, and this is the change, right? So we define it in that manner. And it's positive if 90-degree angle, or the right angle, is decreasing. And this just goes along with the right-hand rule. So it's negative if the 90-degree angle is increasing. And you can also see that on the same block, you're going to have decrease, decrease, increase, increase, because it still has to add up to 360. All right, gamma dot, going further along, is the rate of shearing strain. In other words, it's del gamma del T. And it's also equal to, because they're exactly the same, the rate of angular deformation of that infinitesimal fluid element. All right, so that kind of ends the more mathy part of section 6.1. Section 6.2, we begin talking about the conservation of mass. And although we're going to approach this in a slightly different way, we're back on familiar territory. We know that mass has to be conserved. So we're going to look at this idea in terms of the material derivative, and we're going to go back and take a look at what we looked at in terms of the boundary on the control surface and in the control volume, and we're going to just reduce this to a differential form of the continuity equation. All right, so here we go, where we start by saying that the time rate of change of, this would be essentially a mass term within the control volume, right? We have a density times the differential volume. So now we say, here's the differential volume, dx dy dt, or del x, del y, del z, excuse me, is equal to, this is a volume, times a change in density per time. And if you work out the units or the dimensions, you'll see that those are equivalent. So now we look at the center of the cube, and we look at the right-hand face of the cube, and we look at the left-hand face of the cube. So it's sort of a strange analysis, because we're talking about this differential fluid element, but we're really using finite element methods to analyze the differential element. But it's quite effective. So if we take a look at this, this is on the right face of the cube. This is on the left face of the cube. So we really talk about what's going in and what's going out equal to the change within the cube. So it's the same sort of analysis that we used when we were talking about control volumes, control surfaces, or Reynolds transport theorem, although we're deriving it in a different way. So then we can define the net rate of mass out, the net rate of mass out in the two different, in the y and z directions, and throughout the volume, the rate out. And look what we come up with. Well, we came up with something that we've sort of been messing around with for a while. We have a time rate of change and a convective rate of change. And we've broken it down into coordinate directions. We've expressed it as differential equations. What it's basically telling us is mass is conserved. So that's kind of cool. We came at it from a completely different point of view, but there we go. All right. Now we start talking about the idea of special cases. Equation 627 is steady or unsteady, compressible or incompressible. So equation 627 right here is a very general form of the equation. It's also quite hard to use. It's hard to have most of these variables. But if we can specify it a little bit more simply, and we know, for example, that if we have steady flow of compressible fluids, that the equation is going to look like that, because the del rho del T term is going to drop to 0. That's the definition of, if there's no change in density with respect to time, what we're saying is that's a steady flow problem. And so if we continue on, so let's see, this would be steady flow, and it could be compressible fluid here. This could still be compressible, the equation right here. And then on the next page, they just write it in differential form. And if it's also incompressible, then we know that rho is constant, and it simplifies again. And the du dx, or the del u del x, del v del y, del w del z is just the convective change in velocity component terms. So we're kind of coming back to the same ideas, which is great. That's the way it should be. But what I really want to also mention to you, and I put up a short video clip from YouTube that discusses the fact that velocity potential is related to something we're going to study a little bit later called the stream function through the variables u, v, and w, which are those components of velocity. So I'll definitely watch that little video clip that's up there. It's only 5 minutes long, but it explains that idea very, very well. Okay, so here we go. We have the velocity components, and it asks us to satisfy the continuity equation. So we take a look at this. If we have an incompressible fluid, we know that this has to be true. So we can determine the terms du dx, del u del x, del v del y, just by taking the first derivative with respect to those variables. And then we know that that has to be the del w del z. We don't really know what that is, but we know that it's going to have to be something that's going to make the whole thing equal to 0. So if you plug this plus something else equals to 0, this is what you'll get for the del w del z term. Then to find out what w is, you can integrate it with respect to z. And instead of having a constant, you're going to have a function in x, y, because, of course, with partial differential equations, you don't know if that's going to be a constant or if it's going to be a function in x, a function in y, because x and y both differentiate to 0, just like constants do. But anyway, that gives you an idea of how we work with this. All right, section 6.2.2 talks about polar coordinates. And polar coordinates, we're just going to describe this to you a little bit. Basically, the way that it works is if we have some vector r, or some direction r, at some angle theta from the origin, and we are looking at P, some point. The unit vector along, I call it, the unit vector is going to be E sub r. The unit vector along the radial direction is E sub r. The unit vector perpendicular to that is called E sub theta. And in the z direction, which in this case is coming out of the board, that's going to be called E sub z. So this is an orthogonal coordinate system, but it doesn't stay oriented, fixed in space the way Cartesian coordinates do. It moves as r changes. But basically, we can say then, same expression, that the velocity expressed in polar coordinates is going to be the component velocity in the radial direction times the unit vector in that direction. And similarly for the radial direction, the theta direction, and the z direction. And since those are orthogonal or mutually perpendicular, we have a complete expression for velocity. Now, the development of this, you've seen this before in math class, most likely. I don't know if you've worked with radial coordinates in other engineering science classes. But the derivation is right here, and the expression of those terms in polar coordinates. All right, the last thing that we talk about in this section is the stream function. And the most important thing to remember is that the stream function, which is once again a highly mathematical idea, but the stream function is related to velocity potential through u, v, and w. So watch that little video clip and you'll understand what I'm talking about. But the stream function is assigned this Greek letter, which is psi, more or less. And what we know is that if you have xy flow, so this is simplified form, the continuity equation requires that del u del x plus del v del y must be equal to 0 in order to satisfy the continuity equation. In other words, to satisfy the conservation of mass. We're talking about xy flow, steady, so we're getting rid of that, the ddt terms, and also incompressible. So that makes our rho terms constant, and they fall out of the equation. So this is a very specific case. We have 2D flow that is steady and incompressible, and in that case, in order to satisfy the continuity equation, del u del x plus del v del y has to be equal to 0. So the definition of the stream function then is that del psi del y is equal to u, and negative del psi del x is equal to v. So what that means, and this is the definition, that means that in order to find psi, we could say del psi is equal to u times dy and integrate. We could similarly say that del psi is equal to, say, the integral negative v dx. Okay, and so if we do that integral, then we can find out what the stream function is in a particular set of situations. So the velocity components in a 2D flow field can be expressed in terms of the stream function, right here. And the change in the value of the stream function is related to the volume rate of flow. Right at this point, we're going to have to kind of accept that on faith. We're not really going to be able to analyze exactly what that means. All right. Now, I had hoped to do 2 problems based on this section, on these 2 sections, but this vodcast is already 45 minutes long. The next vodcast, which will cover section 6.4, will be shorter, so on that vodcast, I will take care of the homework problems. So watch this vodcast, number 18, in conjunction with number 19, and you'll get everything that you need for sections 6.1, 6.2, and 6.4, because we'll be skipping 6.3. All right, thanks for your attention, and we'll see you for vodcast number 19 next.